School of Applied Sciences and Humanities to the importance of mathematics. Any walk of life, any branch of life requires some kind of mathematics. Some needs lower level mathematics, and some branches, some fields may require higher level of mathematics. Mathematics is very vast, so it is not possible to anybody to learn all the mathematics. So that is the reason why during your first year undergraduation, we are offering different courses in different branches. Even the same thing is going to happen in second year also. Different branches may get different courses. That is depending on your needs and requirements. But later on, subsequently, I am sure you need many more mathematical concepts which you have to learn on your own. And also from this year, our university is implementing the National Education Policy 2020. So things are quite different from what we did last year. So already you have experience with module 1 and module 2 soon. From tomorrow onwards, you are going to experience the assessment of module 2. So try to compare what you have studied till last year, till your plus 2, and at present in Vigyan, what you people are studying. You should look at it in two different ways. What is the change in immediate what kind of work you have to put in, what is the change, and what are the long-term goals. You decide for yourselves which one is beneficial to you. That's my word to all the youngsters. And as far as our guest Dr. BHASKAR is concerned, he's a good old friend of mine for more than 30 years. And also, he is a person who is experienced in academic area as well as industry. I request Dr. BHASKAR to throw some light on what is the use of mathematics in industry, because he is directly involved when he was working at LG company. What kind of mathematics they are using in industry? I request BHASKAR to spend a few minutes on that also. So with this, I conclude and before that, let me congratulate all the participants in the 7 events we conducted on this occasion, and special congratulations to winners. All the winners will be given the prizes today in this function, and all the participation certificates will be distributed after a day or 2. Okay, bye. See you people.
Thank you, sir. Now I request Senior Professor B. Ramakrishnan sir to give his valuable words.
Respected dignitaries on the dais and off the dais, today we are gathered here to commemorate the great mathematician of India, Vfstr-National, and his contributions can be memorized once so that his contributions can be studied, by the youngsters in future. At an age of 12, he invented his own method of solving quadratic equations. He also gave unforgettable contributions in analysis and infinite series. Ramanujan discovered the theta function and modular function that have an application to the number theory. He worked on partitions, sum of squares, triangular numbers, and the Ramanujan tau function, which is very useful in various calculations in physics and chemistry. And he discovered the formula for infinite series of pi. Ramanujan was well known for his asymptotic formula in the number theory, and this asymptotic concept is very much used in statistics, particularly in the field of normal distribution. And many other contributions were done by him, and mathematics can be treated as a universal language that everyone should know, and also everywhere at each and every level, every individual should know a little mathematics in their fields, and therefore, it has become a universal language in every field today. And my heartiest tributes to the Master Mathematician for his inspiring contributions to the mathematics. And at last, I would like to say, one has to keep learning and improve mathematics language in you and yourself. Thank you for giving me an opportunity to speak 2 words on this occasion. Thank you.
Now I request Dr. N. Srinivasa sir, Dean School of Applied Sciences and Humanities, onto the dais. Sir, please. Thank you, sir. Now I request Dr. N. Srinivasa sir to give his valuable words.
Good afternoon. Today is a very important day. After tomorrow, anyhow, the National Mathematical Day, we have to celebrate. Without mathematics, there is no life. For anything, suppose you want to go to anywhere, general problems I am talking. As a chemist, I say that this is the very important mathematics subject. For I am doing research, but I use so many mathematical applications. Without that, that is not happen. Similar way in any field, even including in medicine, also nowadays mathematics is required. And that's why every student, and particularly computer science and IT, these branches, if you want to grow the highest level president of the company or vice president of the company, mathematics is essential. Those people only grown like that. If you want to do any topic, artificial intelligence or anything, even biostatistics, biology people, these are all very important topics for you. And BSc students, your group is very good. Statistics, mathematics, and computers. Because computer science, I talk with any time, they are asking that this is the best branch in out of all the courses. Then engineering, even engineering also not there. That subjects is required. Engineering also is required. Your subjects is required. That's why we are proposing to start MSc Data Science. Data Science. In the data science, mathematics, statistics, these subjects are not studied by the engineers. our mathematics, statistics, BSc students not studying the computer programming languages. Those languages we are studying in the first year. The BTech students, they are studying about the maths and statistics subjects. Ultimately, all are in perfect in MSc data science by the end of that. Every student should be confident about the statistics and mathematics and as well as computers. Then you will be successful in your life. I gave a small example. One boy, 5-6 years back, he completed mechanical engineering. He joined in software job. He says he got around 35,000 or something. After 1 year, he want to some mathematical requirement is required. Some topics is concept is required. Then I understood. Without mathematics, I am not able to get my salary and the same company I can work. My salary is like this one. Then he decided to resign. And immediately he joined one course in Bangalore and he has done mathematics, statistics, he learned. And after that, his offer was raised to 1 lakh. He joined again. 1 year he worked. After that, why I can work in this field? I learned so many things. Like 4 friends get together, they established their own software company. That's why I'm saying that mathematics, without maths, stat, these things, nothing is there in engineering also. Now every mathematics application is nothing but engineering. That's why you have to learn. If you have anything out there, you have to learn. Ramanujan, he is giving the so many values, and that is now what happened? We are celebrating this thing. But he has done so many years back. But that concept we are using every day. That's why everyone should put interest on mathematics. That is my advice. Without mathematics, nothing is there. Even any subject, you can take any subject, even pharmacy also. In pharmacy also, statistics, biostatistics, engineering, science, agriculture, artificial intelligence using, again mathematics. That's why everyone should try to learn mathematics. And BSc students, you are not feel that I have not done engineering. We are more than that. Why I am saying that? Your subject maths and statistics, your foundation is strong, then you can learn only computer languages. If you learn, you will apply your knowledge on that. Then automatically you can do it. Data science, BTech data science students, what they learn by the 1 year, within a 1 year, you join in MSc data science, you will get that knowledge automatically. And I appreciate regarding the mathematics department and faculty and as well as the organizing of this event. And I am thankful to the particularly the research person is online, it is there, but everyone learn and you can put an interest and listen very carefully and apply your knowledge in future. Thank you very much.
Thank you so much, sir. Now I request Senior Professor Vfstr-National sir to give his valuable words.
Good afternoon to all of you. Dignitaries and delegates, Dean School of Applied Sciences, Dr. N. University, Professor, Chemistry, Dr. P.L. Varma, Head of the Department of Mathematics and Statistics, and V. Ramakrishna, Professor of Statistics, Faculty of Mathematics and Statistics, and my dear students. A very good afternoon to all of you. All of us that assembled here today to celebrate birth anniversary of Ramanujan. Actually, celebrating day on his birthday is one act. Generally, this declaration of National Mathematics Day happened to incorporate the importance of mathematics for every human being. That is the reason in 2012, the then Prime Minister announced this day as National Mathematics Day. And on some occasions, I heard VC was telling, if all our students are thorough with English and mathematics, they are good at every course. A simple statement. If you are thorough with mathematics and English, you are good at every course. So keep this point in mind and remember this day and try to inculcate mathematical thinking process and become bright in your future. Actually, the other resource person online, I forgot, BHASKAR, is also here. We are all awaiting to listen him. Thank you very much.
Thank you, sir. Today we have Dr. Bhaskar HK, Executive Vice President as Chief Guest, and I request Ms. Churamani to read the guest profile.
Good afternoon, everyone. It's a great privilege to introduce our resource person, Dr. Bhaskar H. KOMPELLA, Executive Vice President, Architect, Data Analyst, Healthcare, Philadelphia. He has been holding a double MA in Mathematics and Sanskrit from Andhra University. He obtained his PhD from University of Hyderabad under the guidance of K. Vishwanath. He has worked as research scientist in ISI Bangalore. For 8 years, he has worked as professor in Center of Research and Advanced Studies of National Polytechnic Institute, Mexico. And for 4 years as staff scientist in R&D Enabling Technologies, Austrian, USA. And 10 years as Global Technology Leader in R&D Monitoring and Diagnostic Analytics, GE Water and Processes Technology, Peninsula. He has been worked as Executive Director, Monitoring and Diagnostic System Analytics and Digital Services for 4 years. He has published research papers in many international journals on global analysis like Hamilton Dynamics, Dynamical System, Simplistic Geometry, Chemical Processes, and Monitoring and Diagnostics. He authored nearly 5 books in mathematics, literature, and predictive engineering methods. His PhD thesis was published as monography. Thank you, sir, for accepting our invitation and joining us online.
Please welcome.
Some accent.
ఎక్కడ ఉంది సార్ ఇది arranging this. 1 minute in the applications.
Please welcome him with this round of applause.
Hi everybody, good evening. Can all of you hear me? Okay, can all of you hear me?
Yeah, your screen is visible and you are audible. Please start.
Good.
You can start.
Thank you. Thank you. Okay. Good afternoon, and thank you very much for giving me the opportunity to share some of my experiences with mathematics with all of you, all the youngsters. It's a delight to talk to all of you. And essentially, I'm going to talk about the applications of mathematics. Initially, I thought of just doing only a few applications. Then I was thinking, you're all youngsters entering into your professional, like education, and then you will excel in your careers. So I thought it would be meaningful if I just try to explain why mathematics is so important, and then give a few examples from my experience. So just thanks a lot to Dr. Pelan Verma, who actually invited me, and thanks to all of you for receiving me. And just to give a few words about my background, I never studied engineering. I was a pure mathematics PhD. After finishing PhD, maybe like in 15 years after finishing my PhD, I did MS in computer science from University of Texas in United States of America. But by then I was established in my career. So I did it out of passion to learn computer science. I'm associated with the computer science. I learned my first programming in 1978. So when a lot of people don't even know what programming is in those days. So, but mathematics played a very important role in my career. First 10 years, I spent 10 to 12 years, I would say, in academia. I was working in different universities, in research institutes, doing mathematics research, teaching, masters in engineering, masters in mathematics, all the students. Later, one day, it came to my mind that I need to apply what I'm learning. So I switched to industry. Then I worked in industry more than like 25 years. I think I finished my 25th year last year or so. So with all this, I was really thinking, what should I really talk about? Then I thought I would try to put my perspective. This is all my views about how I thought about mathematics and why it is useful. And it really, really helped me, because as a director of research and development in General Electric Corporation, which is one of the biggest corporations in those days, at least $165 billion corporation. And I'm a mathematician, and all the people who are there in the organization were completely engineers. They're all PhDs in different engineerings, like mechanical engineering, PhDs in electrical engineering, PhDs in chemical engineering, because I worked in water and process technologies, and I worked in power, so lots of electrical engineers. But I was actually directing this group of bunch of engineers in different faculties. How could I do that when I look back? Just because of my mathematics training, my training in physics and chemistry in my bachelor's, but basically mathematics. When they talk about their fields, they always expressed everything in mathematics. So I could really learn and ask a few questions, and I can meaningfully understand what they are trying to say and what they need. As a director, usually give them then whatever they need, more than telling them what to do, because they're all experts. They know what to do. But these are all PhDs from big universities like MIT, IIT. actually General Electric is a huge proponent of globalization in those days. So we have centers all over. So I used to run Shanghai center, and in Bangalore I used to run my group. Like this, in different areas, different locations we ran. But everything happened, and I could really communicate with them because I know mathematics and they know mathematics. They're all very good at mathematics. That's what brought them to that side, that kind of success to really, work in a huge organization, contributing heavily, because not only their own individual faculties like chemical engineering, electrical engineering, and mechanical engineering, mostly those are the people who work with me. Apart from that, they could communicate well because they know mathematics comfortably. They come to the board and write down what exactly they are trying to talk to me. So with that background, that's all the background I have. And let's try to, together, let's try to understand why mathematics plays an important role in our engineering faculty, even in other sciences, not science, mathematics. Mathematics is, there's a debate that whether it's a mathematics is an art or science. So let's not go into that debate, but physicists, chemists, biologists, engineering faculties, everybody is using mathematics. And why so? Let's try to understand. If we exactly know the fundamentals and exactly know why it all happened like that, then we start thinking that, oh, okay, mathematics plays an important role in everybody's career. Kind of thing. So I want to just start with a few sayings on mathematics by different great people. All of you know Galileo Galilei, right? He's a physicist, mathematician, everybody, Galileo. He said mathematics is the alphabet with which God has written the universe. So he was literally strongly believing that mathematics essentially is the language of God. And he literally writes all the statements about the nature, everything in mathematics only. And we need to receive it via mathematics only. Learning mathematics only, we can receive that God's message. That is Galileo's opinion. Then there is another great mathematician, one of the greatest mathematicians ever, we all have in the world, is Frederick Gauss. He said mathematics is the queen of sciences. Then Aristotle, who is almost like the founders of our logic, science, everything, he said mathematics is the science of quantity, because we try to learn anything from nature by measuring quantities. And the mathematics actually is the science of those kind of quantities. Like for instance, if it's electricity current, we just say amperes, and if it's voltage in volts, and if it's energy in newtons, we all know those things. So those are kind of quantities. We actually kilograms, time or distance. All these are quantities. Literally, they're measurements, and it is a science of measurements. That's what he thought. And then there is a person called Hugben. He's a very, very famous guy, and he's a mathematician too. But he said mathematics is the mirror of civilization. Very, very important quote. I always like that quote a lot, because if you see any civilization, you just look at what kind of mathematics that civilization has developed, then you can see that that civilization has some substance in it. Right? Look at Indian civilization. We have a lot of mathematics culture. And go to Chinese civilization. They have a lot of mathematics culture. Similarly, Mayans and Aztecs in Mexico, they have enormous amount of mathematical culture. So wherever you go, Egypt, like that, wherever you go, you see that the cultures have respected learned mathematics. They have their own way of doing mathematics. And so those mathematics literally mirror their civilization. If they have sophisticated mathematics in a civilization, that civilization itself is a very sophisticated civilization. because that is essentially the measure for, like, the sophistication of civilization is mathematics. That's what Hogben says. He has a beautiful book. If anybody wants to read that, then you understand. Then Shakuntala Devi, she always says, there is nothing you can do without mathematics, because everything around you is mathematics and everything is around you is numbers. So obviously, if you are dealing with numbers, you are dealing with mathematics. That's what. These are some of the sayings on mathematics. That's great. People say that. But what are we really, what do we need to understand about mathematics? I have some questions always about mathematics. What is this mathematics? And why mathematics is so important? Everybody's saying it is important, I agree. But why is so important? And what can it do for us? Okay, I learned mathematics. What am I going to gain? What is it going to do for me? If it is not really giving me any benefit, what's the meaning in really learning it? I don't even need to learn. There's some old ancient language which is obscure and nobody is speaking. Do you want me to? Somebody asked me to learn that language. I don't learn it because it's not useful for me. Similarly, mathematics also, I need to understand what it can offer me. Okay. So let's try to answer some of these questions to some extent. Probably we cannot really understand it completely, but we'll try to understand. You are all, I think all of you are studying mathematics from childhood. So it's just go back and start thinking, hey, I learned this much of mathematics. Apart from just going from one grade to another grade, did I really use mathematics in my life? Just ask that question. And then you can really see whether it's offering to you anything or not. But we cannot do that exercise because I'm here like 10,000 miles away here talking to you. So I will try to address that. That's it. But you just think about that and start thinking in those lines. Then you really see where you already applied your mathematics and how you can really improve your life using mathematics and all that stuff. So fundamentally, mathematics looks like a code language, right? It's like a code. And mathematics is the language of scientists and engineers. Obviously, that has been the conception. Because if you go to a artist, probably artists won't speak in mathematics. But if you go to any scientist or an electrical engineer, and if you ask that electrical engineer to say what is exactly Ohm's law, he says voltage equal to time, current times resistance. If you ask a physicist, he says force equal to mass times acceleration. And if you go to a thermodynamist, what is Fourier's law of heat conduction? In one dimension, it is Q equal to minus K dt by dt dx. So he always, see, for instance, these two people are just trying to say simple terms, but this, Fourier law is essentially in a differential equation. So without mathematics, they cannot communicate at all. These fundamental laws, literally, right? We learned all these laws in our high school, college, everywhere. And how many people can really tell Newton's second law in words? No, people say F equal to ma is a very, very easiest way to say what is second law, because that means you are literally speaking a code language where the code is F is force, m is mass, and a is acceleration. And you are saying this mass times acceleration will give you force. And you don't really say that many words. But still, if the other person is a scientist or engineer, immediately that person can understand. That means between scientists and engineers and between the practitioners of science and engineering, we have a code language to really communicate the concepts of very, very, truly, precisely, unambiguously. That means there are, when somebody says F equal to ma, where F stands for force, M stands for mass, and A stands for acceleration, there is no ambiguity at all. You never understand it in any different way than only one way. That is a very unambiguous way. And it's very simple and straightforward. Absolutely. If you see Ohm's law and Newton's law, literally whole electrical engineering is based on V equal to IR, and whole dynamics is based on F equal to MA. They look like innocent equations, very, very simple equations, straightforward equations, but they are pregnant with ideas and meaning. That means if you start analyzing these equations, and if you start analyzing these laws and trying to apply in your real life, they give enormous amount of benefit to you. And you clearly know the electronic revolution, electrical engineering revolution in the last few years. And all this is possible because we actually expressed it in a mathematical language, and we used the mathematical techniques to really understand additional meaning, and to use mathematical techniques and tools to relate all these with another concepts. And we could relate very quickly one law with another law and another principle very quickly, because they're all in mathematical language, and the mathematics has an enormous amount of tools to join them and come up with the new ideas. So each equation that you see, or even a non-equation for that matter, they are pregnant with ideas. So from the day, Ohm and Faraday started electricity, from then to now, so many people were looking at the same equations, but people are coming with different ideas and different, new phenomena, experimentation and different gadgets and all that stuff. That means these innocent equations have a lot of power in them. We need to tap that power by understanding them and applying them in different areas. And mathematics will give you an opportunity to do all those things. That is very important. And it drives innovation. And they're highly reliable. That's one thing. Once you put it in a mathematical equation, if you put an equation equal to in between V equal to IR, it is a highly reliable equation. It is not less than or equal to IR or greater than or equal to IR, anything like that. So it always should be equal. So this gives a high reliability on believing all these statements. And that's all because we have a beautiful code language, which is very logical. And it is essentially telling you the laws of universe when it comes to physics and engineering, science and engineering. Through that, you are essentially communicating. So anywhere in any society, if you want to communicate well, you need a language. Similarly, in the society of scientists and engineers, the language is mathematics. So how mathematics help? Mathematics essentially helps model the behavior of systems. That is the basic importance of mathematics. Mathematics has lots of tools to manipulate and all that. But mathematics helps us model the behavior. Suppose you have a system, you look at a system, and then you try to really utilize in different fields. Then immediately you need to model that. That means what are all the inputs into that system? What are all the outputs in the system? What can I control in that system? Then if I can make a model with these inputs and controls and outputs, if I can create an equation which exactly behaves like that physical system, then you're good. You literally can study it well, because you try to take the system, try to understand the system and convert that system's behavior into a small mathematical model. And then what is the benefit of it? You are understanding the system via mathematics. So you have an equation, and then you can predict how it behaves in future also. Basically, when you are creating a model, your aim is to use that model to predict something. If it is not going to predict anything, that model is a big waste for us, because we don't do any kind of modeling for just look at that. We have to really utilize it. The major utility value of a model is always predicting what happens in future in unknown situations, or at least practically we did not measure something, but the model will tell, hey, I know these 5 things, so the 6th thing should be this. Like that, it should tell us. So that's what we are going to see in a small example. Actually, the descriptions of physical phenomena and experience gained through the physical phenomena. These 2 things will essentially, we utilize these 2 to develop a model, and controlling the physical phenomena and predicting the future physical phenomena is predicting with the mathematical model. Usually math is the cheapest model. Suppose I wanted to build something which is very expensive. Can I really spend just money without really knowing whether it will be a success or not? It's very difficult. Simple example I'll tell you. When I was working in Motorola, I worked in a semiconductor division. In semiconductor division, at that time, Intel came up with 100 megahertz processor. They're going for the Pentium processor. Motorola was really competing with that. And then we were working on a 400 megahertz processor in those days. Now you may be laughing at 400 megahertz processors. What is that? But in those days, it's a very big thing. But we had to really understand how to make a 400 megahertz processor. If you take a silicon slab and start injecting all kinds of impurities like boron and all, and then see the depletion channel will follow, create, and then the transistors and everything, like, all gates can be really created in a silicon slab, and then see whether it works or not. That is a very expensive experiment. Each time, if you're doing an experiment, that actually takes, like, thousands and thousands of dollars, and sometimes it leads to millions of dollars. Then what should we do? We took Mosfet models, which are essentially imitating exactly what's happening in a semiconductor, like, a transistor or something like PNP diode or whatever it is. And we took that mathematical equations, and we thought that those mathematical equations can be tweaked. It's like, okay, let us change the gate voltage a little bit and see whether the depletion will be more or not. Like that, we are trying to experiment completely with a mathematical equation, which is a very cheap thing. There was nothing to do. We just have few like programs written, and we were playing with all those like parameters. So we changed this parameter, that parameter, like that, and we found that, okay, with these parameters values, probably we will reach a better solution. Once we are confident with that model, then we went and asked, okay, make one like silicon slab in which inject these impurities, and let us see whether these parameters can be created in that. If we can create the parameter, whether it works like a 400 megahertz processor or not. So after 2 years, we could succeed. Like that, we do all the experimentation with mathematical models because it is cheap and it gives you insights very quickly. So that is the beauty of mathematical modeling. So to tell you a very simple example, because a lot of you may not know what is a Mosfet model and all, just a very simple thing. Let us take what Ohm did. Okay, this is a resistor with 2 ends, right? That's all. You can see that picture. And Ohm started conducting experiments long ago, thousands, hundreds of years ago. He actually passed these currents from in this wire and started, like, seeing what voltages it is generating. Then he tabulated, because in those days, even to conduct that experiment is time taking and really expensive. So he did for some 5 or 10 values, like I did, and then he tabulated those things. So when he tabulated, there is no line like this. Absolutely, there is no line, right? This line was not there. These are just line, the all points he got. When he got the points, then he just did a curve fitting. And that curve fitting essentially showed him that, okay, voltage is 4 times I, and then that's what he could understand. Then he came up with the law stating that voltage across a conductor is directly proportional to the current flowing through it, provided all the physical conditions and temperatures remain constant. In mathematical terms, it equal to V equal to Ri, where R is a constant of proportionality. In this case, for this particular diode, so for this particular resistor, it is 4 is the proportionality constant. So what he did, he built a mathematical model for a physical gadget. And now he can make it so universal that all he said, this happens every time you do that. And what's the benefit of this? Okay, he could send 0 amps, 1 amp, 2 amp, 5 amp, like that. He could send the current, and he could see the voltage. But the thing is, what happens if when a 3 amp current is passing through? Then immediately this model is predicting that the voltage should be 12 for him. So just by doing few values like this, and now you have a model, and that model can really tell you whatever current I can create I can tell you voltage. What is the voltage you have? I can give you the current, as long as I know the proportionality constant. That is a property of this resistor. So this is how, this is essentially the experimentation he did and gained the knowledge. And then this is the model he created, and this is the prediction he did. So this is a very simple example. Like this, literally, people can do that. So with gadget, you get some experiences. Or with a physical system, this gadget is a physical system through which you gain some experience by doing some experiments, and then you model that. And now, if you become an electrical engineer, you don't see any difference between this and V equal to Ri. They both are the same, because conceptually this gadget is this. So mathematics is giving a different kind of a code for this gadget and its behavior. This behavior is this. Similar, like that, if another example, Newton's law, the second law, force of massive acceleration. Mass in times acceleration is equal to force. He did some experiments initially, and then he came up with this law. So every equation or expression we study in science or engineering is a mathematical model of a physical phenomenon or a physical object. Literally, that's how we started speaking in mathematics about all these engineering and scientific ideas. Literally, we live. So model I talked about, just let me tell you, we really literally live models, right? Because without knowing, we live models. For instance, suppose you have to go for a movie. Movie starts at 5 p.m. and it's 40 kilometers away from your house. And you wanted to go, and you thought of going at 4:20 p.m. That means you have only 40 minutes to go, 40 kilometers. What do? You get on your bike, go, you raise your accelerator, you accelerate it, maybe 60 kilometers per hour. You will not go with 20 kilometers per hour. You know that exactly that if you go 20 kilometers per hour, you cannot even reach there. What you did in your mind, you created a mathematical model with all the intuition you have, mathematical intuition you have in your brain. You know that distance is equal to velocity times the time. So you know that you have 40 kilometers have to be traveled in 40 minutes. That means 1 kilometer per minute. That means 60 kilometers per hour. And your dial on your motorbike shows kilometers per hour. So that's why you raised it to 60. So you very quickly you modeled it without even knowing. So we live mathematics, we use mathematics in every walk of our life. So you just start observing. how many times you are using mathematics. You'll be surprised. So wonder why advanced mathematics. Okay, Bhaskar, this is all just simple time and distance and simple interest and compound interest and all that stuff. Why these advanced mathematics for me? There is a reason to learn these advanced mathematics that we are going to learn. You are going to learn in these 4 years, and what you learned in your intermediate and all. We want to understand nature and record our findings, just like Ohm did, and just like Newton did. Not more than Ohm and Newton did that. Newton's for 400 years formula still we are using. And if possible, we want to guess and predict future behaviors by modeling it in advanced mathematical models, just not like that algebraic equations like F equal to ma. Maybe F equal to ma is not an algebraic equation. A is acceleration, which is a second derivative of distance with respect to time. So it is a differential equation, much more complicated model. So we want to share our achievements so that others can build upon them. I cannot really do everything. Everybody actually sits on the shoulders of their predecessors and try to build upon it. But the people who are there need to tell you what they understood and what they really gained and what exactly they actually created. So there should be a communication methodology of complex physical systems and complex engineering systems that they develop. And for that, we need mathematics also to get advanced a little bit to explain all those complex things. So simple things in simple mathematics, complex things in complex mathematics. There is no other way, right? If you want to talk, you can talk in simply 3,000 words. But if you want to do poetry, you need to learn more language and more artifacts of language. The same thing here too. And we want to improve our life experiences. That's another thing. Once we learn these things, build all these things. For instance, nobody thought of iPhone like maybe 20 years ago, but it is giving a new life experience because somebody dreamt about that and worked on that. And so all that happened because the knowledge was actually recorded and people could connect the dots, and then they bring it to like a next level of experience for us. So it enriches our life. The language mathematics and its tools called mathematical techniques that we learn, like algebra, trigonometric calculus, differential equations, variational principles, etc., which we are going to learn. These are all required because we are actually living in a complex world with complex gadgets, and things will become much more complex, and our understanding is really improving. So along with improving our understanding, communication also should improve so that you can share your experiences and build upon old people's experience. That's why you need to have a sophisticated language also. That's why you learn this one. So what role of mathematics in engineering? A scientist or engineering, it performs what he learned and improvises as per the need of the situation and communicates in the language of mathematics. This is like a rock star, right? Lyrics are always in mathematics, and science and engineering is music, and engineer is the rock star on the stage. So that's how it is. Then, why mathematics prevailed in engineering? First question, okay, I all agree, but why did they start with mathematics? There is no other go. As Galileo says, God has written in mathematics everything, and we need to receive it in mathematics. Firstly, if you see all basic laws of nature, they're all modeled in mathematics, right? Newton's law, Hooke's law of elasticity, Fourier's law of conduction, first and second law of thermodynamics, Faraday's law of induction, Gauss' law, Kirchhoff's laws, current law, voltage law, Ohm's law. Take anything, every fundamental law that we are literally exploiting and creating this huge technical world. Everything started with those fundamental laws only. We all know that. Without that, any fundamental, there is no fundamental law. We cannot really build anything. But all those fundamental laws are captured via mathematics only. That means every law had to be modeled in mathematics. Otherwise, they could not proceed. just by saying the definitions and saying the relations in long sentences, they could not really do anything, because we need to do a simplification, straightforward, unambiguous. You saw all those things. That's how they need to communicate, to quickly get exchange the ideas. And that's the reason mathematics has to do all that. They have to do in mathematics. And when these laws are used in combination to develop engineering ideas, it became inevitable to continue mathematical language, tradition, tools, right, to advance further. That's why mathematics was a dire need. So people may be thinking, hey, nowadays I don't need to worry about learning all the calculus, because I can go to Mathematica and I can just ask it and it will tell me all those things. And a hydrodynamic modeler can think that, oh, we have computational dynamic modeler, so I can just go and plug in my numbers and it will give answers. All that is good as long as that program is working well. But sometimes what happens is, the programs that are written were not enough for your need. Then, unless you know how those program is working, you cannot improve it. But there are some challenging situations where all these standard tools and computation tools and all that the people are building, they are not enough when you are innovating something, right? If you are doing routine jobs, they will be okay. But if you are innovating something, those tools will not work. That's when you need to go back to your mathematical foundation and understand the equations that they were using in the tools and in their APIs or some whatever that is, application programming interfaces. Then you need to really go further. So that basics, if you want to excel, that basics in engineering should be at your it may not be at fingertips, but you can do by reference. But at least when you look at that, you should be able to analyze the equations. You should feel familiar. For that, you need to learn mathematics and get that familiarity. That's it. So engineering practice is a treasure of applied mathematics, frankly. I'll give you a few examples. You take a small dwelling unit of like 2 people can live in this small house. 350 plus people can be lifted into air by a 300-ton aircraft. Imagine how much weight it is actually taking and flying across the Atlantics and Pacifics and all that stuff, a Boeing aircraft. The funny thing is, when I'm designing my building, or when I'm really designing this like an aircraft, literally I'm using mathematics, because all the basic principles are in mathematics, and I just put them together in combinations. For instance, in this, I take all the electrical engineering basics and mechanical engineering basics and civil engineering basics and aerodynamics engineering basics, and so many basics I need to take, combine them into one huge idea called a flying Boeing, right? So there are stresses, strains, tension, compression forces, load balances, strength of materials that we are building, aerodynamics, energy efficiency. All this is modeled in mathematics. And if you see a manual, if you go to aviation, go to any big company like McDonnell Douglas, which actually builds all these things. See, their manuals, even online, there are some manuals with thousands and thousands of pages of mathematical equations. And based on them only, they build all this stuff. Just like a small building, you see a blueprint with all those measurements, everything done. And I don't know how many of you saw a floor plan in a blueprint. Previously, they used to do that, but now CAD and all are changing so many things. But this is one of the, a great amazement. To my great amazement, when I see these two, there is enormous amount of difference between these two to build. A civil engineer and an aeronautical engineer together should build this, whereas a civil engineer can build this. But when it comes to here, an aeronautical engineer, electrical engineer, civil engineer, mechanical engineer, materials engineer, so many people have to come together, bring their faculties, and bring their knowledge, bring their mathematical models, and combine them and build it. So it is a huge applied mathematical feat initially. Once those things are perfectly done, when it goes on assembly line and people blindly build it, but for the inventor, that is a big challenge. So there's an enormous amount of mathematics used in this. The second one, this is where I really worked in General Electric. So you say a centrifugal pump that pumps water for home. You know, there's a small well. From that well, you put a pump there. It actually fills in your overhead tank, and from there you literally start using at home. There is a very small pump, an impeller. There is an impeller design and suction, and it has to create a head. And head means the water, how much height the water goes. Those are some of the things. And a simple model. You see this simple model I gave you, how they really build a mathematical model for such a small pump, and how they really create a functional schema, a block diagram. And you see there is a small differential equation that is built as model for this. And they try to solve this differential equation. There is a PV curves, there's pump curves and all those things, pump and volume, pressure volume curves. And then with that, they can really model all sizes. For a small size to a huge size pump, they can literally use the same model, and sizes may vary according to your need. But basically, the pump mathematical model is the same. So one model you build, then more or less all the centrifugals or pumps of any size, it can be built. Whereas if you go to a gas turbine that can generate thousands of megawatts of power, like 4,000 megawatt power, see this thing. It is amazing, because if you go to a gas turbine building plant, it is like a 1 mile. I speak always in miles. Sorry, maybe 2.5 kilometers, 3 kilometers distance building, a long building. And on the one side, they take a big round cylinder of steel metal, nothing else. And then they start carving it. All the machines will automatically come and carve. By the end, it comes, it looks like this. This is actually carved out of one big, steel beam, like a cylinder, huge cylinder. And these blades are properly built, and on each blade, the vibrations are properly calculated. The turbine, when it turns, if a blade actually vibrates a little more than it is supposed to, the whole turbine will blast. See, imagine how much of precision they have to have on each blade. You can see these blades, right? And the blade has to, certainly when it is really rotating in a very, very high pressure gases, these wings will certainly, these blades will actually vibrate, and they should not vibrate as they want. So all this precision engineering, imagine the mathematical models and consider on the differential equations and everything. For a small pump, we have this much of mathematics. Can you imagine how much mathematics that will go into this huge turbine, where it is a mechanical engineering feat to build this sculpture? This is like a shilpam, right? Sculpture. And there's a lot of electrical engineering wire work inside, because once it starts generating wire, like an electricity, the electricity should be pulled out of the turbine, and essentially it has to be supplied to the power plants, at least the grid. So imagine they use differential equations, linear algebra, probability, optimization, linear programming, and Fourier transformations, and all kinds of things. So much of mathematics. When you are getting when you turn on a switch on the wall, the light is coming, and you need to understand so many engineering and scientific brains with so much of mathematics has created this wonder for you in your house. It's like an effortless thing for you. But if you start imagining what all these people did for you, you really feel so grateful. And imagine all of you are going to enter into such a beautiful profession where you also do this kind of wonders, and so many people will be inherently grateful for your services. So get very excited about this opportunity of learning these things. And these are the years where you can really learn fast and need to learn also all these kind of mathematics. Then simple thing, a water filter. Nothing, it's like flow rates, surface area of filter bed, maybe reverse osmosis. And if it is a kind of an ice plant, they are small plants. But you see a fractional distillation column in a hydrocarbon industry, the huge column where there's evaporation, condensation, phase transitions. That means the petroleum crude starts at the bottom. And as it is, the temperatures are getting hotter and hotter. Actually, the petroleum crude goes up and it actually leaves different compounds that are existing in this petroleum crude, and people will be collecting them through pipes. So kerosene, tar, ultimately gasoline, which is essentially our petrol. But the petroleum crude is at bottom. So how to model all this stuff? You need to have so many principles that need to be really taken care. All those principles are again mathematics, and they are interrelated here. So use differential equations, recurrence relations, linear algebra optimization. So there is a huge model developed for this fractional distillation column. And the crude that goes into crude is actually the crude oil that is taken from earth. So some oils are very nice. So the column will, the fractional distillation will be done very, very quickly. If you buy oil from some Gulf, it is essentially coming from a big bed of sand. So the oil comes very neat and clean. Suppose you buy it from some Siberian forest or some desert, like, areas or some rock beds. The crude has its sulfur in it, it has all silica in it, and so many contaminants. You need to process that. And if you put such crude into the same tank, because you cannot build one tank for one crude. Today you buy crude from one country, and from another day you buy from another country. But same fractional distillation column should work for all crudes, right? That is the goal. And there's how to treat that crude so that the fractional distillation will become very efficient, and the tar, gasoline, and everything can be kerosene, everything can be taken out of that crude for utilization. What is the model? So very, very simple principles like evaporation, condensation, cooling, and collecting, but and phase transitions. But using them very, very intricately relating them and using them and modeling them. We cannot send all crudes when we are building this fractional distillation column. Maybe we have one or two crudes to test out, but all these crudes should work ultimately, right? That is the goal. Am I sharing it? Can everybody see my screen? Hello?
Yes, sir. Yes, sir.
Okay, sorry. Yeah, I'm coming to end. So yeah, just I want to be sure about it. Yeah.
So everything is visible and audible, no problem.
Okay, thank you. Please let me know if there are any hiccups. Okay. Yeah. So yeah. So see from a small water filter and an ice plant to a fractional distillation column, which is much more complicated thing. So this is kind of complexities you deal with when you go into a industry. Suppose you got a job in somewhere in who is that? Who is a petroleum lead in India now? So he has Ambani has a big petroleum plant. You got an excellent job with high pay, and you're going to work with fractional distillation column. There's so much of an excitement. Understand all these models and day-to-day operations you can do very efficiently. You can generate monitoring and diagnostic controls so that you can completely see how the plant is running. Literally, how the plant is running, we used to see on a big screen. So all those things you can build once you are an engineer and we understand all these principles. And even to create this small filter, the factory has so many models. That's one thing. And so I actually covered one civil engineering example, one mechanical, one chemical, and one so the electrical engineering example. Simply, I'll tell you. I don't describe too much because so much of mathematics here. This is the big monster of mathematics. So you have seen ordinary phones with cables. Then you have seen these kind of like a little more sophisticated digital things with microwave towers, and then you went into this, the bigger towers, right? And then we went to satellites and iPhone. All this progression. Similarly, radios and televisions, and then satellite radios and all that stuff. All this revolution is completely a mathematical wonder too. It's not only the electrical engineering wonder or electronics wonder, it is a mathematical wonder too. At the base of everything, there is mathematics. Just you can simply imagine a sound will go in like a wave. Light will go like a wave. Once there's a wave, certainly you need to use a Fourier equation, Fourier expression of the wave, because waves are actually literally expressed as combinations of sin nx and cos mx kind of thing. And then there's a Fourier analysis there. And then there is Z transformations to really make your mathematical calculations much more simpler. And there are probabilities, linear algebra, differential equations. Obviously, differential equations, because there's electromagnetic theory, and electromagnetic theory, even if you see the basic principles of Maxwell equations, they're all partial differential equations. You know that. And there's complex analysis, especially multivariable calculus, maxima, minima, and all kinds of mathematics goes into this particular engineering faculty, electrical engineering. So very, very exciting, and mathematics and electrical engineers learn enormous amount of mathematics, no doubt about that. They're as good as any other mathematicians, because all these are absolutely needed for them to really understand the physical phenomena. And again, there is industrial engineering people who will build it, and who will help building this. Then packaging engineering people will pack it. You get a iPhone in a beautiful bag, like in a beautiful box nowadays. All those things, but the basic stuff. So this is a very, very exciting era in which we are living, and we have enormous amount of opportunity to really, experiment with these kind of things. And what happens is, if you try to understand the mathematical, the fundamentals strongly in engineering, you need mathematics to do that, and you do that. You comfortably manipulate these laws. See, knowing law is different from manipulating the law to come up with a new innovative solution. When you're trying to manipulate the law, you need to do some mathematics to manipulate it, because everything you cannot really do as an experiment in your lab, because that is very expensive. But as much as possible, you try to do simulations, everything using mathematics, or nowadays a laptop. It can do wonders for you. You can do all those things, and then you can come up with innovations. Fundamentally, you need to understand small innovations lead to very good, achievements, no doubt. But the big leaps are always the challenging ones, where you need to have very fundamental, knowledge about engineering and mathematics. That is very, very important. So some of the people, especially the engineering in the last 100, 150 years, did real wonders, frankly. Can you imagine when we have a telephone, United States to Europe, how do they used to do telephone in those days? Telephone is a cable, right? The cable, this phone is connected to a cable here. In United States, and similarly there will be another phone with the cable in Europe, and both needs to be connected. How are they connected? There are no satellites in those days. There is no wireless communication in those days. Literally, they took a cable of close to 4,000 miles and put it in the Atlantic Sea. At the bottom of Atlantic Sea, you have all those cables even today. Can you imagine that many miles of cable to make it, take it and actually put it in on the floor of the sea and connecting on both continents and talking. Is it not a beautiful, a great wonder in those days? Just imagine how people could do that. That is the kind of conviction every engineer should have. So later they thought that, oh, this is not a sustainable solution. How do you do? Then they started using, trying to come with different communication methodologies. Now the satellites are literally taking orbits around the Earth and giving you communication left and right. You can talk from any part of the world to any part of the world without even one wire. See, this wonder happened with just in 100 years. So these kind of things they could do only because of these strong fundamentals. And imagine this technology, cable technology to wireless satellite technology, there is no comparison at all. So many areas were joined here when it came to here. This is only with a sheer electrical engineering feat. This is another engineering feat of all engineerings. So people are converging. Once we are converging, complex ideas can be built from different dimensions, different engineering dimensions. Those complex ideas should be recorded. How can they record? With a complex mathematics. That's all it is. So finally, I don't want to say too much about computer science. For instance, computer science and mathematics, I think it's a bro relation. That's it. They're brothers. That's it. Because computer science from the beginning was actually practiced by mathematicians. Even the very and some physicists. I cannot forget von Neumann, who's a great mathematician and physicist who did that. So if you see the computer architecture or functional programming, like you're doing Python, C++, Java, and all C#, whatever, all the functional programming and distributed systems and the so-called machine learning and artificial intelligence nowadays, these are essentially full of mathematics. They're all the fundamental branches of computer science is like 50 to 60 to 70% mathematics only. The remaining is computer science related ideas, but more mathematics. Mathematics has been playing a big role from the day one in computer science. And even as a computer scientist, you need to learn discrete mathematics, probability, combinatorics, logic, number theory, graph theory, calculus, differential equations, linear algebra. So many things you need to learn. To do, as a computer scientist, you know that you need to simulate so many things. As I was telling, doing a physical experiment is very expensive. So if somebody makes a mathematical model, and if you want to really run it, previously manually people used to do for days and days and days. Now with the computer, within few hours you can do millions of passes. So system simulation, improving problem solving techniques, and creative effective algorithms, and graphics, data mining, data analytics, predictive and prescriptive analytics, right? The predictive and prescriptive analytics is becoming a big thing nowadays, in the healthcare. If you have all the health data of a person, you can predict, okay, this guy is going to get diabetes. So because he's going to get diabetes, let us ask him to do exercises from now onwards. So that is a prescription. So like that, machines can, literally computer can advise you. That's what kind of analytics we are building. And speech recognition, that when you talk, immediately the computer can identify which person that is. Similarly, pattern recognition, we know that. If you throw a photo into internet, it will essentially give you all the photos which are looking like that. All those kind of things, search engines and everything. For all this, you need all these kind of mathematics. They are not as sophisticated mathematics. The need here is not as sophisticated as in the core engineering. Remember that. The core engineering mathematics is really solid mathematics. It is on par with any great mathematics. Here, the mathematics, you just really learn some basics and try to apply it intelligently. And only when you're going to data analytics and all, probably you will be using some kind of a sophisticated mathematics, but not like electrical engineering and mechanical engineering. The core engineerings have their own needs. Now, let's come to the end. How good a mathematician should every engineer be? Do I need to become a great mathematician to really study engineering? What is this guy saying? Do I need to study engineering or mathematics? These kind of questions you can ask. They are genuine questions. I fully agree. There is no perfect answer for this, but for sure you need to learn it to get your degree. Everybody knows that. Otherwise, you cannot get a degree. But mathematics help you in your career for sure, because you saw all the evidence. And if you develop a passion for learning mathematics, you will stand out as a good engineer. So, very simple thing. Suppose my car broke down, and if I go to a small a car mechanic shed, maybe a car mechanic who did not study anything, but he just learned from his father or brother how to repair the cars, he can repair it for me. Wonderful. But suppose he could not repair. What should I do? I need to go to an automobile engineer who will look at the design of the car and find out, oh, these are all the problems. And for these problems, okay, these are the solutions. Or I need to go to manufacture, whatever it is. But you see the difference? A person who is routinely doing the maintenance doesn't know much. He's okay. He is useful and he's good. He's good at that profession. And if there are 50 problems, he can solve all the 50 problems, even in his, even if he's sleeping. That's all good. He's an excellent mechanic. But when the 51st problem comes, that mechanic cannot handle. That's where your engineer enters into the picture, who has the knowledge of models, has the knowledge of the automobile. That's where your additional value that you are going to provide. Most of the time, what happens is in careers, people learn engineering and they still live like mechanics. That's what I'm saying, car mechanics. No, you need to excel in it, and you need to have your niche for that. That's the kind of passion you need to show as an young person, and learn. And if you want to become a good engineer, learn engineering subjects absolutely perfectly well, but aided with good mathematics. Bottom line, you are an engineer first and mathematician in addition. Remember that. First you should be an engineer, then a mathematician, because they are all pursuing engineering faculties. So what good mathematics can do to you ultimately, if you learn mathematics seriously, you start developing algorithmic thinking. That is one good thing about mathematics. You start thinking logically, algorithmically. That means you don't jump here and there, think things very jumblingly. Mathematics, as you go on, learning mathematics and practicing mathematics, your brain thinks like an algorithm. This step first, second step, third step, fourth step, like that. It brings you an algorithmic thinking. Once you have the algorithmic thinking, suppose you are asked to present some engineering idea, you can present it exactly. Exactly means to the point, whatever you are thinking, you can exactly express that. And logically, systematically, you don't do that clumsily. Okay, first I need to tell this point, then this point only, because logically they follow one after the other kind of thing. And you can do it completely without leaving in one detail. You can completely say that in mathematics. So mathematics will become a vehicle to do this, because it is generating an algorithmic thinking in your brain. Sorry, it's 4 o'clock in the morning for me. And once you have that thinking, if you develop, presenting the ideas, you become a clear thinker. The value of clear thinker is highest in industry. In industry, you are respected if you are a clear thinker. You may not be a great thinker, but if you are a clear thinker, that means you talk systematically, put the point exactly, talk logically, without any gaps, and very clearly explain things, then you are a big winner. And so the clear thinking with a focused presentation let you excel in your profession. But algorithmic clear thinking with sound engineering basics along with mathematics will make you an innovator or inventor. That is the thing. So so everybody should strive to become an inventor. You don't need to invent huge things, even a small thing of your own you need to have. And just like a poet, though he reads everybody's poetry, he actually tries to put his own poems in his own feelings in his own poetry, and makes a small book. He may not write huge books, but small book, but it itself is a great achievement for him. Similarly, you can become an inventor. And I'm not talking about money part. I am not really worried about money. Eventually money comes to you if you have passion. There's no doubt about that. People may talk about bad luck, good luck, and all that. Let's not go there. But if you have passion, if you put your work, money comes eventually. No, there's no problem at all. And then with that, I will stop, but with a little bit of apologies to you, some of you. Keeping time in mind, actually, I did not touch some of the other engineerings like biomedical engineering, industrial engineering, environmental engineering, and finance engineering. There are several other engineering branches. Probably the students from those engineerings are present here. My apologies to you. I did not give you examples from your fields. Firstly, because I never worked in those fields that much. And secondly, the time also. But this general discussion about importance of mathematics and its applications in engineering essentially is applicable to even these biomedical, industrial, environmental, and finance engineering also. With that, I thank you very much for giving me an opportunity to converse with you. And I'm very grateful to all of you for listening to what I was explaining, and what I'm expressing. These are all completely my own feelings about mathematics.
You have many more things to say, but I feel, in fact, I will take some other opportunity to invite you for another lecture. And next time when you are in India, but I would prefer to come here and physically. Now I request our visitor, Dr. Raghunathan, to say a few words.
Thank you so much, sir, for your very interesting and very apt lecture today on the eve of the first anniversary of Srinivasa Ramanujan. And this university has been celebrating every year the National Mathematics Day with a lot of fervor and enthusiasm, participation of all the stakeholders, irrespective of the branch. Right from mechanical engineering, the hardcore engineering, to science, applied sciences, and the biotechnology, all those professionals join and to make this day very eventful and memorable. I thank you so much. I've been listening for the last 45 minutes without even moving an inch from my seat. It was so, what should I say, you pitching at the absolutely correct level for first year students, very easy to understand, with a lot of pictures that gives a very direct relevance of mathematics to the engineering student. Thank you so much, sir. As Professor Verma has very correctly said, you must visit. Seeing is believing. Seeing is believing. We request you wholeheartedly to please come to the campus and spread this infection of mathematics amongst all the engineers.
Thank you, sir. Thank you. Thank you very much.
Once again, I thank Dr. Bhaskara for giving a lecture at 2:30. It's now around 4 o'clock for him. Okay, thank you, sir.
Thank you. See you. Bye. Bye, all of you. Yeah.
Okay, bye.
Goodbye. Yeah.
Okay, friends, we would like to conclude this program today at this moment and postpone the prize distribution to some other day because of some unforeseen events. Okay, I'm sorry for that, but there are a few things which are not in our hands. So we'll at an appropriate occasion will distribute the prizes to all the prize winners. I'm sorry for that. Okay, thank you.